Okay, the last thing we did is we showed that, the following are equivalent. I is invertible, or you can multiply, I is invertible if and only if you can multiply it by some other ideal and get a principal ideal. And then, we saw some examples of this last time. What's the deal about invertible ideals? Well, here's one of the deals. The set of invertible ideals of R forms an ability. This is called, and I'm gonna, uh, of non-zero principal fractional ideal is a subgroup called prim R. So, how do you multiply ideals? You multiply ideals just the way you multiply ideals, but now we have to, so you have I, J, is the ideal I, J. And as you might guess, suppose I and J are invertible, then the inverse by J is the product of the I inverse times J inverse. It's easy to verify that this works, right? And prim R, this is the set of things of the form omega R, omega non-zero elements. Okay. Notice that every ideal in prim R is invertible, right? Because and so, in a certain sense, you have all the invertible ideals, right? Let me give you an example of a ring Z, right? It turns out that it turns out that every fractional ideal of Z is actually invertible, and in fact is principal. There's a lot of noise, right? In INVR for Z. I mean, it basically looks like prim R. And so we find a class group of R. So basically what this does is this crushes out the noise. You take all the invertible ideals and you consider all principal ideals to basically be the zero element, right? So it turns out, for example, if you have a principal ideal domain, the class group is trivial because all invertible ideals turn out to be principal. So you're measuring nothing. So I'm just going to make this plain here, but for any ring of algebraic integers, start here. E. Integer. We have these rings of algebraic integers. Let R be C join the square root of D if D equivalent to 3 mod 4, Z joined with 1 plus radical B. We've seen this thing before. This is called quadratic ring of integers. It is integrally closed, and in fact, we'll get to this in a moment. It's a Dedekind domain, and it turns out that all non-zero ideals, fractional or proper, are invertible. Which is actually pretty rare. I mean, if you've got your garden variety ring, you expect there to be ideals that are not invertible, but these are very nice. And in fact, this is one of the reasons why number theory is cool. This class group is always finite, right? And in fact, the class group is trivial if and only if you have a principal ideal domain. If you think about this in terms of factorization, the class group is trivial if and only if the ring of integers is UFD. UFDs and PIDs are the same in this particular class of rings. In general, they can be different, but within these types of domains, they're the same. PID is equivalent to UFD. And there's other things about the class group that actually tell you things about factorization. For example, the class group is either, well, so the class number, that is the order of the class group, is less than or equal to 2, if and only if every factorization into irreducibles has the same length, for example. Let me give you a theorem here that I think is perhaps a bit surprising when you first look at it. Theorem 937. Any invertible ideal is finitely generated. What does it mean to be an invertible ideal? It means when you multiply, given any ideal, you can construct its inverse, I inverse. That's just a set of things, and in fact, it's also another fractional ideal if I is. It's invertible if I times I inverse is actually equal to R. This condition forces the ideal to be finitely generated, which to me is not very clear at all from the definition. Now, dangerous bend here, make sure the other direction is wildly untrue. If you have a finitely generated ideal, then it's not necessarily invertible. Although I can't think of one class of finitely generated ideals that are always invertible. Principal, there you go. For example, if they're principal non-zero. So let's prove this. This is kind of a surprising result. Suppose I is invertible. Then I times I inverted is equal to R, right? Okay, so what does this mean? The cool thing about, of course, notice that I inverse is always contained inside R by the construction of it. So I inverse is a proper ideal of R. Well, I inverse is an ideal that's contained in R. It could be the whole thing. So the operative thing here is for I inverse to be R. This means there exists alpha 1 up to alpha n and I, beta 1 up to beta n in I inverse, such that alpha 1 beta 1 plus alpha 2 beta 2 plus alpha n beta n is equal to 1. Right? That has to happen because you got to have the 1 in there. Now, I'm going to make the following claim. I claim that when you find this relation here, then I is actually generated by those alphas that you pick, can be generated by this. Let me first point out that certainly I, whoops, oh wait. Right, because each of those alpha i's are in there. So as an R module, the R module generated by alpha one up to alpha n is contained in I, right? The tricky part is the other way, right? Why is it true? The other way. Let me recall for you very quickly, that might help in the other direction. Prove, recall I inverse is the set of beta in K such that beta I is contained in R. So let's just recall that for a moment. Now to show the other containment, let uh, let gamma be an I. Okay. Now take this gamma and multiply it by this equation here. And what I get is beta 1 gamma alpha 1 plus beta 2 gamma alpha 2 plus beta n gamma alpha n is equal to gamma. Right? Now notice that each of these things in parentheses is in R because beta 1 is in I inverse and gamma is an I. So when you multiply those two together, it has to be an R. So gamma so my arbitrary gamma is an R linear combination of alpha 1 up to alpha 1. So I is contained in this, so I is equal to alpha 1, alpha n. And so as it's finitely generated, the proof is okay. Any questions on that? Okay, so here's another kind of important thing about invertible ideals. Let R be a domain, I a fractional ideal. If I is invertible, then I is locally principal. I'm gonna have to take it. And that is to say that I plus P principal for all prime ideals. Um, Um, if I is finitely generated, then the converse is true. So, let me make a remark there. If R is a quasi-local domain, and what I mean by quasi-local, I don't know, I use this terminology, unique maximal ideal. Back talk about local domains, or not quasi-local. This is one of the weird things about sort of terminology creative algebra. Quasi-local means it's got a unique maximal ideal. That's terminology I use. Because local, when you hear the word local outside of Hungerford, that usually refers to quasi-local and Noetherian, right? So if somebody like Carrie uses the word local, then what she's talking about is actually something that is also Noetherian. If R is a quasi-local domain, so the only hypothesis unique maximal ideal is any invertible ideal of R principle. This is a very important result, and it follows from this theorem here. So invertible means principle. We've seen examples. In fact, I think I used z adjoint with the square root of -5 last time and gave you examples of ideals that were not principal, but they were invertible. So you can bet your bottom dollar it wasn't a quasi-local ring. Yes.
And an IP application for the localization as well?
Yeah, so let me tell you what this means here. So that's a good idea. Let me recall what P and R be prime, with some prime idea, then R localized to P, unfortunately, is a set of R over S, where S is not in P. Right, yeah, I apologize for that, because when you see the terminology R sub S, that usually means numerator from R, denominator from S. When the subscripted thing is an ideal, it means everything not in there, right? So why is it called this? Well, because it turns out that what this does is this flushes every ideal in R that is not contained in P. And so the ideal, the original P prime here, what this construction does is if you have your original R and it's got some prime ideal P, then when you go up to R localized to P, this prime ideal is now the maximal ideal, right? So it chops off everything that intersects what's outside of P. So it leaves only P. Everything outside of here is units. All right, so it makes it into a quasi-local ring. And so the notation I sub P follows the same thing. This is the set of alpha over S, where alpha is in I and S is not in P. So basically RP is the localization here where you turn everything outside of P into units. And I is just the extension of I up to that ring. So it's every fraction that you can form, numerator from I and denominator outside of P. Okay. So let's do this thing. Okay, so let's see why this is true. So let's look at the forward direction because the reverse direction has a condition on it. Well, the first thing is, let me actually do this, let me start. Do I care about this? I don't know if I even need this, but, let's, send this, so, we can assume that I is an R. I mean, of course, fractional ideals don't have to be an R. But remember, one of the things about a fractional ideal is I can hit it with a single thing and knock it down into the ring. So I will just assume that I've hit this with that single thing and knocked it down into the ring just for ease. If you like. Note that if I is invertible in R, then IS is invertible. This is any multiplicative set, not necessarily the complement of a prime ideal, right? Because, this is a routine. See if you can verify this. This isn't hard to do. So this reduces us to showing that a fractional ideal of R localized at P is invertible if and only if it's principal. An ideal non-zero P is invertible if and only if notice of course any principal ideal that's not zero is invertible, so the burden is really on the other direction here. Showing that if you're invertible principal in this particular situation. So to that end, let's suppose that I is invertible and R localized at P. And suppose that I is generated by A1 to AN. Of course, we're using the previous result because we know that if it's invertible, it has to be finitely generated, right? So we've got that going for us. Choose generators of I inverse, and you can clearly do this by the proof if you look back at the previous result. B1, B2, Bn such that A1, B1 plus A2, B2 plus AN, Bn is equal to 1. Right? All of this comes from the previous results. We've got a finite number of generators, and we can choose the generators by inverse so that that happens. Now, notice that of course, each one of these little terms over here has to be an R because this guy is an I and this guy is an I inverse, so their product has to be within R, right? And I claim that at least one of them has to be a unit. Must be a unit. Anybody know why?
If none of them are units, then they're all in the maximal ideal, so their sum is also.
That's huge, right? This has a unique maximal ideal, right? Any quasi-local ring, so our local SP has a unique maximal ideal. If none of these are units, then they all have to be in the maximal ideal. Which is actually P localized P, but it doesn't matter what you call it. So, one is in P localized P, which is the top of it. So let's say that A1, B1 is a unit. Was it A1, B1 is in here? Well, I claim that A1 is good enough to generate I. Notice that, of course, A1 is contained in I. That much. On the other hand, suppose we have an arbitrary element called X and I. So suppose X is I. So I'm gonna do a little prestidigitation with this unit condition here. So X, well, so it's A1, B1. So we know that A1, B1 is a unit, that's our hypothesis. So let's write X as U inverse. Yep. Notice, of course, that this is an equality because A1 and B1 is the same thing as U, which cancels. So this equality holds. And what is the significance here? Well, notice that B1X is in R, right? Because this is in the inverse, so this is in R. Therefore, A1 is RX for some R is R. So, and then we go. So, if it is invertible, then it's locally principal. And for the other direction, we have to assume finitely generated, and I'll illustrate that in a moment. For the other direction, now suppose I is finitely generated. So I want you to see what goes on in this proof. So suppose that I is finitely generated and locally principal. That is, IP is principal. For all P and R prime. So you guys okay with the?
We don't want to prove that I is generated by A1.
Mhm.
So we want to prove that every element in I is a product of A1, right? That's
Yeah, that's right.
why we conclude that A1 is equal to Rx.
Well, this is the, so notice, this element's an R, U inverse is an R, so A, oh, because I just miswrote it, I didn't say it, yeah. That's, sorry about that. Okay, so let I inverse be the inverse of I. So remember, what we want to do is with the inverse of any ideal can always be constructed, you just build it, it's just everything in the quotient field that blasts I back into the ring. We want to show that I inverse is actually equal to I. So for any prime ideal, P and R, we have that I localized P is a principal ideal. Of course, verbal. Remember, I'm starting with the assumption that I is contained in the ring just to make this a little bit easier. And also note that if I is finitely generated, this does exactly what you would hope it to do. This is for a general multiplicative set, not just the complement of the prime. When you have I localized at S, the inverse of that is the localization of I inverse. This is just an easy set containment to figure out. So for all prime ideals, P so for all prime ideals, say P and R, we have that I localize P, I localize P inverse is RP, which is inverse localized P by that previous bit. So you look at I inverse, it's contained in R, of course, and if it's contained in any maximal ideal, we have so I inverse must equal R, because this product cannot be contained in any maximal, any prime ideal, and of course, prime. Now, my question before we go to the end game here is, one of the things that puzzles me is, okay, so I've done this proof, and I assume that I was finitely generated, right? Maybe I'm just not very good at proving stuff, which we can make an argument very easily that way. Maybe there's something amiss here, and maybe the theorem works without the assumption of finitely generated. I just didn't find a good enough proof. But I will set your mind at ease here by giving you an example. Start with this might be an old familiar thing. This is a set of A over B where B does not apply to B. A, B, and Z. B, not apply. So you're like, you all are familiar with this, right? Like, for example, Z localized at 2 is all rational fractions with an odd denominator. Now, there's a, so let's start here at this level. And it turns out I've only got one prime p here. Well, one non-zero. Now, what I want to do is I'm going to go, there's a theorem due to, I don't know who it's due to, but it's famous in Gilmer's book, where you can build quadratic extensions of a ring and basically control what happens to ideals. And this is especially good if you have just a finite number. And here we have only one prime ideal. We could go to an extension, we'll call it R1, first step, where P so at this level, I've made P split into two primes. So at this level, I have P, P1, Q1. You can define a quadratic extension that makes this split into two things by sagaciously picking the square root of each one, so to speak. Now let's go to the second level. And what I'm going to do in this extension, now I've got two primes to deal with. This guy, I'll leave prime. I don't do anything to him. And this guy, I break up the same way I did before. Like that. Now, at the R2 stage, and that's a terrible two, isn't it? R2 stage, I've actually got 1, 2, 3 primes. Right? Now I'm going to go to the R3 stage, and I'm going to leave these two prime, and I'm going to split this. So, for example, at this stage right here, P is equal to Q1, Q2, Q3 times P3, right? Now, at this stage, I've got 4 primes. As you might guess, the next one, I'll leave these 3 primes and split this one. All just doing this with quadratic extensions. And I continue this forever. Now, it turns out what happens is, I can tell you exactly what the prime ideals here are. This one. Well, P1, I guess I can take this, at the next level. Equals P2, Q2. And so forth, so on. Anyway, so here's what I have. We'll call this the ring made by all this. This one has, this is almost a principal ideal ring, because the primes of R Q1, Q2, Q3, forever. And there's one more. Everybody see what it is? And finally, the idea generated by P1, P2, P3. Every time I add a new generator, the previous one becomes redundant, right? Because once I throw in P1, I don't need P anymore because P1 divides it. Once I throw in P2, but I need them all because the process never stops. Right? Now, if you look, we'll call this big one here. We'll call big boy here, M. If you look at of course, these prime ideals are easy to deal with because they're all principal, so they're locally principal, but that's all good. What happens when this ideal, of course, is not finitely generated because no matter what you pick from these P's to generate it, the next one divides the rest of them, it's bad. What happens when you look at this maximal ideal and R localized it in? It's generated only by P. Because guess what? All of these are outside of the maximal ideal, right? So when I localize here, I turn everything that's outside of this maximal ideal into a unit. So in that localization, these are all units. So this is all poppycock right here, right? Because P is P1 times Q1, but Q1's a unit, so P and P1 are associates, right? P1 is Q2, P2, but now Q2 is a unit, so P1 and P2 are associated, so P is associated with P2. So all of these, even though they're different here, when you localize it, it's like a big fat accordion. It collapses all down to P because these are now varied only by units. This is a good example of an ideal that is locally principal, but it's not invertible. And its problem is it's not finitely generated in the original range. So that's kind of a fun example. Okay. Any questions on that? Okay, so I have just a perfect timing, I think. One theorem, and I'll tell you what a Dedekind domain is. And that can be my advertisement for community valve in the fall. This is a rather important one. Let R be commutative with one. Then R is equal to the intersection of R localized at M. R is as M ranges over the maximal ideal. So if you take R localized at M for all the maximal ideals and intersection, you get R.
That doesn't work also with the localization, with the intersection of all the localization by primes.
I'm sorry, what's that now?
That doesn't work too with the intersection of all the localization by primes.
Oh, when you intersect, yeah, so that's actually, see, this intersection, when you localize it a smaller prime, it's actually bigger, so you're just kind of throwing in extra stuff that aren't gonna make any difference, right? So, yeah, that's a good question, though. So. So we know that R, can be identified as contained in R localized at M. Okay, so that makes this containment pretty easy. For the other containment, what we're gonna have to do is actually look at an ideal here. Let X be in the intersection of M and let I be the set of S and R, such that SS, is contained in R. If I am proper, then I is contained in M for some maximal ideal. Because every proper ideal must be contained in the maximal ideal. But if this is so, then X is not in this Rm. Right? Because if you have Sx, so if I is in M, then this means that Sx in R implies S is in M. Therefore, X equals R S implies S is in M, and that's a contradiction because X is supposed to be in this intersection. So you have to be able to write it as a fraction R and S with S not in M. Right. So therefore, I can't be contained in any maximal ideal. So I must be R. Therefore, 1 is in I, so X is in R. And there you go. I'm going to give you this final definition here. And I'm not going to prove it, but again, I can tell you this can be kind of a teaser for me to develop because I'm sure we will walk this path. Here is my generalization of factorization to ideals, if you will. Let R be an integral domain. Following are equivalent. Number 1, every non-zero fractional ideal of R is invertible. 2, every proper ideal I in R, non-zero, is invertible. So you can reduce this to just like the ordinary ideals. 3, every non-zero ideal is uniquely a product of prime ideals. That is to say, you might not have unique factorization into elements, but you have unique factorization of ideals into prime ideals. And 4, R is Noetherian, integrally closed. And the Kroll dimension of R is less than or equal to 1. So that means either the dimension of R is 0 and it's a field, or the dimension is 1, in which case all non-zero primes are maximal. And finally, R is Noetherian. And R localized at M is a valuation domain. for all M, maximal. Any domain that satisfies one of these and hence all of these conditions is called Dedekind domain. So that is the end of 8520. I've enjoyed having you. If you're having trouble getting caught up in your homework, give me a holler. And also, don't forget to do the evaluations. Okay, any questions? All right, well,